Yes, the 625 amps rating at 120/208 volts is typically a per leg rating. To elaborate further, let's delve into the details of transformer output amperage ratings in three-phase systems, specifically concerning the 120/208 volt configuration. When a transformer is specified as having a 625 amps output at 120/208 volts, it generally refers to the maximum current that each leg or phase of the output can handle continuously under normal operating conditions. This is a crucial aspect to understand for several reasons. Firstly, in a three-phase system, the load is distributed across three phases, often labeled as A, B, and C. The 625 amps rating indicates that each of these phases can supply up to 625 amps simultaneously without exceeding the transformer's design limits. Secondly, the 120/208 volt configuration is a common type of three-phase system where the voltage between any one phase and the neutral is 120 volts, and the voltage between any two phases is 208 volts. This configuration is widely used in commercial and industrial settings to power various types of equipment and appliances. Thirdly, it's important to distinguish between the phase current and the line current. In a three-phase system, the line current is the current that flows through the conductors connecting the transformer to the load, while the phase current is the current that flows through each phase winding of the transformer. In a Y-connected system, which is typical for 120/208 volt distribution, the line current is equal to the phase current. Therefore, the 625 amps rating directly corresponds to the line current that each conductor must be able to carry. Now, let's consider the input side of the transformer, which is rated at 278 amps at 480 volts. The relationship between the input and output amperage is governed by the turns ratio of the transformer and the power equation. The power on the input side must equal the power on the output side, assuming ideal conditions, meaning no losses. The power equation for a three-phase system is power equals the square root of 3 times the voltage times the current times the power factor. So, to calculate the approximate output power, we can use the input values power equals the square root of 3 times 480 volts times 278 amps times the power factor. Assuming a power factor close to 1, the input power is approximately 231 kilowatts. Similarly, on the output side, the power can be calculated using the output values power equals the square root of 3 times 208 volts times 625 amps times the power factor. Again, assuming a power factor close to 1, the output power is approximately 225 kilowatts. The slight difference between the input and output power is due to the losses in the transformer, such as coal losses and copper losses. These losses are typically small, and the transformer's efficiency is usually quite high, often around 95% or higher. When sizing conductors and protective devices for the transformer, it is crucial to use the per leg amperage rating. For the output side, this means using the 625 amps value to determine the appropriate conductor size and overcurrent protection. According to the National Electrical Code, the conductors must be sized to carry at least 125% of the continuous load current. Therefore, the conductors on the output side must be able to carry at least 1.25 times 625 amps, which is approximately 781.25 amps. This requirement ensures that the conductors are not overloaded and can safely carry the continuous load current without overheating or causing a fire hazard. In addition to conductor sizing, it is also important to select the appropriate overcurrent protection device, such as a circuit breaker or fuses, to protect the transformer and the connected equipment from overloads and short circuits. The NEC provides guidelines for selecting the appropriate overcurrent protection device based on the transformer's impedance and other factors. Typically, the overcurrent protection device should be sized no larger than 125% of the transformer's rated current. Therefore, for the output side, the overcurrent protection device should be sized no larger than 1.25 times 625 amps, which is approximately 781.25 amps. However, the specific requirements may vary depending on the application and the local electrical codes. Furthermore, it is essential to consider the voltage drop in the conductors when sizing them. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting the voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is necessary to use conductors that are large enough to carry the load current without significant voltage loss. The length of the conductors also affects the voltage drop. Longer conductors will have a higher voltage drop than shorter conductors for the same load current. Therefore, it is important to consider the length of the conductors when sizing them. In summary, the 625 amps rating at 120/208 volts for the transformer output is a per leg rating, indicating the maximum current that each phase can handle continuously. When sizing conductors and protective devices, it is crucial to use this per leg amperage rating to ensure that the electrical system is safe and reliable. Additionally, it is important to consider voltage drop and other factors to ensure that the equipment operates efficiently and without malfunction. Remember to consult the NEC and other applicable electrical codes and standards for specific requirements and guidelines. The input rating of 278 amps at 480 volts represents the current drawn from the supply to feed the transformer. This input amperage is directly related to the transformer's kVA, or kilovolt ampere rating, which is a measure of its apparent power capacity. The relationship between voltage, current, and kVA in a three-phase system is given by the formula kVA equals volts times amps times the square root of 3 divided by 1000. For the input side, this would be 480 volts times 278 amps times the square root of 3 divided by 1000, which equals approximately 230 kVA. This kVA rating represents the amount of power the transformer can handle without exceeding its design limits. The output side of the transformer, with its 625 amps per leg at 120/208 volts, must also correspond to approximately the same kVA rating, accounting for any transformer losses. So, on the output side, 208 volts times 625 amps times the square root of 3 divided by 1000 equals approximately 225 kVA. The difference between the input and output kVA reflects the transformer's efficiency, which, as mentioned earlier, is usually quite high. The per leg rating of 625 amps is critical for several reasons in practical applications. Firstly, it dictates the size of the conductors needed to connect the transformer to the load. Conductors must be chosen to safely carry the expected continuous current, typically with a safety margin as specified by electrical codes such as the NEC. For example, NEC Table 310.15b16 provides ampacity ratings for various conductor sizes based on insulation type and ambient temperature. Using this table in conjunction with the 125% rule ensures that the conductors are adequately sized to prevent overheating and potential fire hazard. Secondly, the per leg amperage is crucial for selecting the correct overcurrent protection devices, such as circuit breakers or fuses. These devices are designed to protect the transformer and downstream equipment from overloads and short circuits. The overcurrent protection must be sized appropriately to allow for normal operating current while still providing protection against faults. The NEC provides guidelines on how to size overcurrent protection devices for transformers, taking into account factors such as the transformer's impedance and the type of load it serves. Thirdly, the per leg amperage is essential for load balancing in a three-phase system. Ideally, the load should be distributed evenly across the three phases to minimize current imbalance. Uneven loading can lead to increased losses, voltage imbalances, and potential equipment damage. Therefore, it's important to carefully plan the distribution of loads across the three phases, taking into account the per leg amperage rating of the transformer. Now let's look at the practical implications of this transformer specifications. Imagine a scenario where this transformer is feeding a commercial building. The building has various loads including lighting, HVAC systems, and receptacle circuits. Each of these loads will draw a certain amount of current from the transformer. To ensure that the transformer is not overloaded, it's important to calculate the total current drawn by all of the loads on each phase. This calculation should take into account the demand factors for each type of load, which are factors that estimate the percentage of the load that is likely to be in use at any given time. For example, lighting loads may have a demand factor of 100%, while receptacle circuits may have a demand factor of 50% or less, depending on the type of equipment that is likely to be plugged into them. Once the total current on each phase has been calculated, it can be compared to the transformer's per leg amperage rating of 625 amps. If the total current on any phase exceeds 625 amps, the transformer is considered to be overloaded, and steps must be taken to reduce the load or upgrade the transformer. In addition to calculating the total current, it's also important to consider the harmonic content of the loads. Harmonic currents are currents that are at frequencies that are multiples of the fundamental frequency, which is typically 60 Hz in the United States. Harmonic currents can be generated by nonlinear loads, such as electronic ballasts, variable frequency drives, and computers. These harmonic currents can cause a variety of problems, including overheating of transformers and conductors, voltage distortion, and interference with sensitive electronic equipment. To mitigate the effects of harmonic currents, it may be necessary to install harmonic filters or use transformers that are designed to withstand harmonic currents. These are referred to as K-rated transformers. Furthermore, grounding is a critical aspect of electrical safety and performance. The transformer's grounding system must be properly designed and installed to provide a low impedance path for fault currents. This helps to protect people and equipment from electrical shock and damage in the event of a ground fault. The NEC provides detailed requirements for grounding electrical systems, including transformers. These requirements cover the size and type of grounding conductors, the location of grounding electrodes, and the bonding of metal enclosures. In summary, understanding the per leg amperage rating of a transformer is crucial for ensuring the safe and reliable operation of electrical systems. This rating dictates the size of conductors, the selection of overcurrent protection devices, and the balancing of loads across the three phases. Additionally, it's important to consider other factors, such as voltage drop, harmonic content, and grounding, to ensure that the electrical system meets all applicable codes and standards. When working with electrical systems, it's always best to consult with a qualified electrical engineer or electrician to ensure that the work is done safely and correctly. They can provide guidance on the selection of appropriate equipment, the proper installation methods, and the applicable codes and standards. Remember that electricity can be dangerous, and it's important to take all necessary precautions to protect yourself and others from electrical hazards. When dealing with transformers, it's also important to consider the environmental conditions in which they will be operating. Transformers generate heat as a byproduct of their operation, and this heat must be dissipated to prevent overheating and potential damage. The NEC specifies the maximum ambient temperature for transformers and provides guidelines on how to direct the transformer's ampacity if the ambient temperature exceeds this limit. Additionally, transformers should be protected from moisture, dust, and other contaminants that could damage their insulation and reduce their lifespan. In some cases, it may be necessary to install the transformer in a ventilated enclosure or to use a transformer that is specifically designed for outdoor use. Finally, regular maintenance is essential for ensuring the long-term reliability of transformers. This maintenance should include periodic inspections to check for signs of damage or deterioration, as well as testing to verify the transformer's performance. The testing should include measurements of the transformer's voltage ratio, insulation resistance, and winding resistance. Any problems that are identified during the inspections or testing should be addressed promptly to prevent further damage or potential failure. To recap, the key takeaway is that the 625 amps output rating, especially at 120/208 volts, signifies the amperage available on each leg of the three-phase output. This understanding is fundamental for safe and effective electrical design and installation. Always refer to the manufacturer's specifications and relevant electrical codes for detailed guidance.